Here we will discuss about fundamentals of soft set theory. So all the lectures are prepared. So here is the shortest introduction about a study of fundamentals of the soft set theory. So here we will discuss definition of soft set and some of their operations used in soft set like union, relative union, complement, relative complement, intersection, and other properties. So this is a basic introduction about soft sets. So here, here is some introduction about soft set theory. So concept of soft set was first formulated by Moldsev, 1999, as a complete new mathematical tool for solving problem dealing with the uncertainties. So after this definitions uh, of soft set is a parameterized family of subsets of a universe set. Means this is soft set deal with set of parameters and onto the universal set. So after this, Maggi et al. Present a detailed theory study of the subset, which include the subset and superset of the subset. So first of all, there is definition, and after definition, there is some properties like subset. Similarly, superset of a subset. Equality of subset operations on subset such as union operation, intersection operation, and or operation among others. These all operations are presented by Maggi et al. So after this operation, they also studied and discussed the basic properties of the operations. And after the Maggi, Pei, and Mayo redefined subset and intersection of they redefined subset and intersection of the subsets and discussed the relationship between the subset. After that, Ali et al. Introduced some new operations such as the restricted union, restricted intersection, restricted difference, and the extended intersection of two subsets and discussed their basic properties. So after that, these operations and some properties, we will discuss Kagman and Giancarlo developed source matrix theory and successfully applied to the decision making. So here, first of all, there is definition after some properties and restricted properties, and after that, Kagman and Ingeniolo developed source matrix theory and successfully. Here, in this process, soft matrix theory has been developed. After that, Babita and Sunil introduced the concept of soft set relation and functions and discussed many related concepts such as the equivalence soft set relation partition of soft set. We will define all these definitions step by step in our next part of this paper. And after that, Babita and Sunil further worked on soft set relation and ordering by introducing the concept of antisymmetric relation and the transitive closure of a subset relation. After that, Yang and Guo introduced the notions of the antisymmetric closure of a subset relation obtained with the proof some result involving them. After that, Siskin and Artagan, Gay and Yang fully gave some modification in the work of Maggi et al. And introduced some new concepts. So we will discuss all these concepts step by step in our next part of the paper. So here, if we will discuss from starting, so these are preliminaries. First of all, definition of the subset. Subset means simply there is a separate video about subset. Here we will discuss only a short introduction about the subset. So subset is the parameterized family of you can say let U be the initial universe set and E be the set of parameter or attributes. Means we can say the properties of a thing with respect to U. That P of U will be the power set of the universal set denoted by the power set and a subset of E. We will take some parameters which we can say A is subset of E. Up here F of E is called the subset. We can say that what is f of a? F of a is mapping from a to a is a set of parameters a to p of u. In other words, a subset over u parameterized family of subset of u. So there is we can define f of a as f of a is equal to f of e such that here this type of element will be present in this soft set. F of E will be the element of power set. So what are elements of E? E are belonging to E. So F of E will be empty if E does not belong to A. So here we will discuss this by example. So here is example related to this. So example number 2.1. Here we will take a universal set and this is universal set U having elements h1 up to so on h6 be a universal set consisting of the six houses under consideration e1 e2 e6. This is a set of parameters and there are total six houses. We want to select some house or some houses. So how we will select? So each universal set consists of all the houses and is the set of parameters. Means we want to find costly or cheap house and near to the city and very close to the airport and some other properties like modern, wooden or expensive. So these are some attributes. E with the set of parameter with respect to u where each E1 this is simple. So we want only three properties like E1 expenses, E2 beautiful and E3 cheap. There are total six houses and these are some properties and we want only expensive, beautiful and cheap. So I select a subset of E, only three elements. So here we will find the houses which include property 1 means expensive. So in expensive, there are two houses. Similarly, second property E2. E2 parameter includes beautiful, so only three houses are very beautiful. Similarly, E3 is cheap, so only three houses are cheap. So these are attributes, and if I write this into a single notation, so this will become as f of here f of a will be equal to h2 h1. So this is relative to f of e1. Here are three methods to write this subset. Here is related to f of e2. Similarly, this is related to f of e3. So you can write f subset as in this method. You can also write subset in this method, and you can also write subset by third method, which is given as f of A is equal to E1. E1 parameter includes f of E1. Similarly, E2, this is domain, this is our range, this is domain, this is our range. So we can put the value of f of E1. So this is H2, H4. Similarly, E2 is equal to H1 to H5. E3 will be equal to. These are 3 to 4 methods to write a subset. So after definition of subset, we will write properties of subset. So here are some properties or and operations on the subset. All these topics are discussed in a separate video, so we can see from a separate video. So other property is definition soft subset or soft. equal. Similarly, we will write two sort set f of a and g of b be the two sort sets. So f of a will be sort subset of g of b if a set is subset of b and all e belongs to a. F of e and g are identical approximations. So this is simple property a subset b, then f of a will be subset of g of b. Similarly, f of a is a sort equal. There is another definition like equal sort set, like equal set. So f of a subset of g of b and g of b subset of f of a. So both of the sort set will be equal. This is definition of sort subset. Similarly, sort subset redefine sort subset will be equal to, if I write declare. So here is definition of sort subset. So what is definition of sort subset? Here we will discuss. Here is the definition of subset. So first, for two sort sets f of a and g of b over a universe U, we can say that f of a is a sort subset of g of b, f a subset of b, and for all e belongs to a, f of e subset of g of b. This redefinition of the sort set. So there are some examples related to the sort set. So if I write example number 2.2, so this is equal to, let u be the six, consisting of six elements, and E is the set of parameters consisting of five elements, and I select only three parameters, E1, E3, and E5, which are subset of B, and B is E1, E2, E3, and E5. Two set of, this is set of parameters, this is also set of parameters. So we will find sort sets relative to A and relative to B. So f of E1 is equal to U2, U4, f of E2 and f of E5. So G of E1 will be equal to U2, U4, G of 2. So this is sort set, and then f of A subset of B, since A subset A and B. So what is definition and what is example f of a? What are elements of a? We had defined elements of f of a in our previous example 2.1. So there are elements of g of e2. So according to our definition, f of a is a sort subset of g of b, because a is subset of b, because this is a1, e2, e5, and b is e1, e2, e3, and e5. So another definition, equal sort set. So f of a and g of b both have not equal element, so both are not subset of each other, so f of a not equal to f of b. Similarly, there is a remark 2.1, f of a and g is the subset over a common universe U. F of a is subset does not imply that every element of the f of a is an element of g of b. Therefore, definition of classical subset does not hold for subset. So we cannot say that if f of a is subset of g of b, so every element of f of a does not contain in g of b. So there is an example related to this. After that, some other definitions are as node set. So simply this is simple definition, node set. If E is the set of parameter even to up to so on en with the set of parameters, the node set of E denoted by node E is defined by node E. This will be only, we will write node in front of all the elements. So this is definition of node subset. Let E be the universal parameter, A and B are subset of B. Then these are properties of node set. Proposition. This is De Morgan law. We can also define De Morgan law in sort subset and sort sets. So not A and A union B is equal to not A intersection not B. These properties, you can use these properties in your FSC section. Uh, chapter number 2 in FSC part 1 mathematics. So you can also define De Morgan laws by sort sets. So here is another definition, which is as let U be the set universe, E be the set of parameter A subset E, then F of A is called the relative null subset with respect to A, denoted by if element of F of E are 0, then this is called relative null sort set. And if element of F of E is a whole set U, then this is called the relative whole set. These are simple definitions. And similarly, the relative whole sort set with respect to E denoted U of E is called the absolute sort set over the U. There are some examples related to the topic. Let E the set of parameter A is a subset of E, then F of E two elements are F of E three elements are 0, F of E element E four elements are universal set D. Then the subset F of E F of A E two U two U. So here is example 2.3. E is the set of parameter. A is a subset of E such that f of E2 is U2 and U4. F of E3 is empty. F of E4 is universal set. So you can skip in writing f of E3 because this is empty. So if B is E1, E3 such that the subset G of B is E1 empty, E3 empty, then the subset G of B is relative null sort set such that G of B is equal to phi of B. So if C is E1, E2 such that H of E1 is U, H of E2 is U, then the subset H of C is relative whole sort set because this is uh, U and this is also U. So these are relative sort set. Similarly, there is preposition, some properties relative to the sort sets. Properties of relative sort set, there is definition of complement. So here the complement of subset f of A is denoted by f of A. Here is C. C shows complement is denoted by f of A. F of A means subset. Here is complement. So f of A complement will be equal to f of C, and simply its complement will be converted into negation or not. Here in our previous topic we had discussed this. So f of C from not A to P of U is a mapping by the f of C alpha, where is the U minus f of not alpha for all alpha belongs to not of A. So this is only inverse process or inverse mapping like in our subset. So here elements will be U minus f naught of A. The relative complement is the relative complement of subset f of A denoted by f of A. R means relative is defined by f of A R. F of R A, where f of R is from A to P of U is a mapping given by f of A. Similarly, this is f U minus f of A. This is f of naught of A. U of U minus f naught of A, and this is f U minus f of A. So here is example related to the complement. So U be the universal set, E is the set of parameters. Then suppose A is E2, E3, E4, subset of E such that the sort set f of A. This is our sort set. Then f of AC. This is f of A. We want to find complement of f of AC. So this will be equal to this is E2. So not of E2 are elements. Not of E2 means which element are not included in this set. So not of E2 are U1, U3 and U5. Similarly, not of E3 will be whole element, whole set U because E2, E3 is not here. So if element is skipped here, so this means that is empty mapping. So E4 is U, so this will be E4 empty. So we had skipped E4 empty. So similarly, the relative complement f of a r will be equal to E2. This is E2. So elements which are not included here are U1, U3, U5. Similarly, U3 elements not included are U. So because here E3 maps onto the empty set, so E3 will be uh, U minus empty will be equal to U. So there is preposition related to the complement. Double complement is equal to simple subset. Double relative complement is equal to simple subset. UA of C will be equal to relative A. Phi of A will be equal to U relative of A. Complement will be equal to for empty. This shows empty. So for empty complement is equal to empty, and empty relative complement is also equal to empty. Whole complement and whole relative complement both are equal to empty set. So there are some operations on the sort set. So first of all, definition 3.1 is the definition of union. So simply you have to learn the definition of union. If f of a and g of b denoted, f of a subset is union of g of b subset. This is union. Then the subset h of c, where c is equal to a union b, and for all e belong to c. Here in SOT union, first of all, we will consider C, which is the union of A and B. So H of E will be equal to F of E, and G of E, F of E means E belongs to A minus B, and G of E means E belongs to B minus A, and F of E union G of E means element will consist of E, which is intersection of both of the elements. So the intersection of a and G of B denoted by F of A intersection. G of B is the sort set where C is equal to A intersection B, here C is A union B, here C is equal to A intersection B, where A belongs to C, here also E belongs to C. So H of E will be equal to F of E or G of E, as both are the same set. So similarly, this is AND operation. Similarly, this is OR operation. Here, simple will consist of A cross B. Here, this will also consist of A cross B here, but this is intersection. This is union. In AND operation, there is intersection. In OR operation, there is union. So intersection redefined. Similar intersection redefined. Extended intersection. There is definition of extended intersection. Similarly, restricted intersections, restricted union, restricted difference, restricted symmetry difference. Here, these are simple definition, but we will apply the properties of subsets. Here is a definition of symmetric restriction. So here are examples related to the our previous definitions. U set of parameters, universe E, a subset of A, then f of A consists B and G of B, another subset, then G of B is f of A union. This is union. So if I define union, elements of f of A is E1, E2, E3. Similarly, element of B are E3, E4, and E5. So in union, we will write E1, E2, E3, E4, and E5. In intersection, we will write E3 because E3 is common. This is restricted. In E3 is equal to here H1, H2, H3, and here E3 is H3, H4, and H5. So we combine both. E3 will be equal to H1, H2, H3, H4, and H5. Similarly, the third f of A intersection G of B will be E3. Both have common properties H3. F of A and extended intersection G of B will be equal to E1, E2, E3, E4, E5. Similarly, extended intersection is like the union property, and so this restricted difference will be equal to E3. So here E3 is H1, H2, H3, and here E3 is equal to H3, H4. So if we subtract both, so 3, 4, 5, and here is 3, 4, 5, and there is 2, 3. So this will be here difference 3 and 5 after subtraction. So if I subtract E3 and E3, so this will be H1 and H2, H3. So this will become H3 and H5. So this is f of a symmetric difference g of b f of a and g of b f. So this is an operation. This consists of uh, cross product A cross B element. So similarly, this is f of A or g of B. So how you can write f of A and g of B? So this is E1, E3, H2, E1, E4. We will write E1 with E3, E4, E5. Similarly, E2 with E3, E4, E5. Similarly, E3 with E3, E4, and E5. Similarly, H2, H2, H4, H1, H3, H3, and these elements. Similarly, f of A or g of B. So this will be E1, E3, E1, E4, E1, E5, E2, E3, E4, E5, E3, E3, E4, E3, E4, E4, and E3 and E5. These are properties like insets, idempotent properties. Similarly, identity properties, domination properties, complementation properties, double complementation in involution properties, exclusion properties, contradiction properties, De Morgan properties. Similarly, these are absorption properties, commutative properties, similarly associative properties, distributive properties. These are some remarks. Then after some remarks related to the sort set relation and function. Cartesian product of the sort set is the Cartesian, how to define Cartesian product of two sort set. Cartesian product of two sort set f of a and g of a will be written in the form of H such that a cross B will be equal to P of U cross U, and H of a b is equal to f of a cross U of B for all a b belongs to a cross B. Here we will write example, then this topic will be clear. H of AB is equal to H1 Hj, Hi belongs to f of A and Hj belongs to G of B. Elements of the Cartesian product will be into the form of ordered pair. So set relation. So here we will discuss definition of domain of our first element of the this Cartesian product will be domain. The second element will be range. So inverse will be if we change domain into range, so this will become inverse of the sort set. Similarly, let U be denoted the set of the people. This is example 5.1. U is the 10 people that denote the post professionals given by the A, accountant, doctor, engineer, teacher, represent A. Here are some parameters A1, A2, A3, and A4. B the people which are B, SC, B Tech, MBBS, MS, B1, B2, B3, B4 represented by the B. So here is A, here is B, here is universal set, and the sort set F of A is given by this is our sort set. So we can consider any kind of the sort set. Here we consider f of a. This is sort set. Similarly, we consider g of b. So then, if we want to find the relation between them, then f of a1 cross g of b1, f of a2 cross g of b3, f of a3 cross g of b3, f of a1 cross g of b. For here, domain will be equal to this element range will be equal to R inverse. This is here relation is f of a1 cross g of b. So how you can write f of a1 cross g of b? This is f of a1. This is g of b1. We will apply to the all elements of p1 with p1, p1 with p2, p1 with p6, p1 with p8, p1 with p10. Similarly, f of a1 with g of b2, f of a3 with f of a1 with g of b1, f of a2 with g of b2, f of a3 with g of b3. So this is called our relation. So this you can see that f of a1 cross g of b1, f of a2 cross g of b3, f of a3 g of b2, f of a1 cross g of b4. So these are some examples. So another definition of complement of R, union of R and Q, intersection of R and Q. There is example related to the topic. So after that you can write reflective property, symmetric, transitive property. Are these properties are basic properties of sets, equivalence, identity. So here is example related to the cross Cartesian product and their properties. After that, we will convert our topic into the matrix representation of a soft set. Soft set, soft matrix. What is soft matrix? Here we will only write how to write soft matrix. This is a relation from U cross E to 0, 1, where uh, 1 will be answer when U and E belongs to R of A, and 0 will be answer when U and E does not belong to R of A. Here is matrix. Here how to write soft matrix. Let U be the set of parameter universal set and E be the set of parameter. A is E1, A subset of each set of parameter we are selecting from our whole set of parameters. So E1, E3 and E4. So here if f of E1 is equal to U3, U4, f of E3 is equal to empty, and f of U4 is equal to U1, U3 and U5, then the sort set f of E is given by this is sort set. Because this is empty, you had skipped here. So f of A E will be equal to E1, E4. The relation of f of A is given by the R of A. This is relation given by because E1 with U3, E1 with U4, similarly E4 with U1, E4 with U3, E4 with U5. This is our source relation. So if you want to find the matrix, so here is matrix related to this because U1, U2, U3, and this will be equal to 1. Similarly, this will be equal to 0, this will be equal to 0, 0, this will be equal to 1. Here I is equal to, when I and j are same, then this will be equal to 1. Otherwise, this will be equal to 0. So I is equal to 1 to 5 and j is equal to 1 to 4. 1, 2, 3, 4, 5. Here are 5 rows and 4 columns. So this is A11, A12, A13, A14, A14. Similarly, how you can write this matrix, we will look. Here is our relation and what is definition of soft matrix. Our answer will be equal to 1 when U and E belongs to R of A, when U and E belongs to relation. So here is U1 and E1 0, U2, U3, E4 and U4, E5. We will look at how to write this matrix further. So the definition of special soft matrices. These are some properties of soft matrices. Similarly, here are some example related to the this is 0, B, E2, E4, B, F, B, E2 is equal to U, F of B, E4 is equal to U also. So this will be then B of ij is a B universal sort matrix given by B I J. So this is E2, E4. Similarly, this is identity, this is sort submatrix, this is dominated comparable proper sort subset. and restricted proper subsets. These are some basic union, intersection, complement, difference properties of subsets. These are M and N, M union and M intersection, and these are some basic definition you can apply here. N M minus M. So properties of sort matrix operations. Here are De Morgan laws had discussed here. So here one topic is unclear, that how to write a matrix. So first of all, our rows consist of U set of universe. So here are five elements: U1, U2, U3, U4, and U5. If I write by using uh, so this is U1, U2, U3, U4, and U5. This is E1, E2, E3, and E5. So U3 is, this is U3. So U3 includes E1. So U3 includes E1. So this element will be equal to 1. So U4 here is U4. So U4 includes E1. So first row and first element will be equal to, sorry, fourth row and first element will be equal to 1. So this is U1. So this is U1, and fourth element, this is E1, E2, E3, and this is E4. So U1, E4 element will be equal to 1. So similarly U3, this is U3, and fourth element will be equal to 1. Similarly U5, this is U5, and fourth element will be equal to 1. All other elements will be equal to 0. This is how you can form a sort set from elements, and then sort relation from these sort sets, and then apply to form a matrix from these sort set. So this was our paper related to the sort set. Here we will discuss sort set definition, some basic properties of sort set operations, and at the end sort matrix. So next time we will discuss another extensions of sort set in our next lecture.